Hello friends, today we will discuss about Boolean algebra. This is the very fundamental topic in digital logic design or digital system design, which is very useful for the students, those who are appearing for GATE examination and also who are preparing for undergraduate level examinations from various universities. Now let us discuss about Boolean algebra in detail. This Boolean algebra is identical to the mathematical algebra, which is invented by the scientist Boole. This Boolean algebra is made up of several parameters. The first parameter is set of elements. The second one is set of operators and a number of unproved axioms or postulates. Whereas in mathematical algebra, already we have some idea. It is also having the set of real numbers and the algebraic equations. And to represent these algebraic equations, we have to use several operators. And to simplify these algebraic equations with the help of the theorems or postulates, so that it is having several theorems or postulates. Similarly, the Boolean algebra also consisting of set of elements. The set of elements used in this Boolean algebra are only zeros and ones, because the Boolean algebra which uses only binary values. Now, let us move to the set of operators, the next parameter. Set of operator means which specifies the type of the operators used in equations. The equations used in Boolean algebra, we called it as Boolean equations, also called as Boolean expressions, just like algebraic equations in normal mathematical algebra. Now, the several operators in Boolean algebra are and, or, not. These are the basic logical operators. Whereas in mathematical operators, the several operators are addition, subtraction, multiplication, division, and so on. In the same way, in Boolean algebra, the basic logical operators are and, or, not. These are the basic operators. With these basic operators, we can develop the other operators also. Those are NAND, NOR, XOR, and XNOR. These are nothing but additional operators. Now let us discuss about the basic operators. The first one is AND operator. It is similar to multiplication. That means A and B. Suppose if we take the two numbers A and B, we have to ANDing together with the dot symbol. So dot means ANDing operator, which is identical to the multiplication operation in mathematical algebra. Next one is OR. It is similar to addition. That means A plus B. A plus B means, suppose if we take the two numbers, this plus operator which indicates the ORing of A with B. The next basic operator is NOT. NOT means complementation or inversion. We can apply NOT operator only for the single variable. If A is the input variable, then the complement of A is A bar. So it should be denoted with the A bar symbol. The next operator is an AND operator, which is obtained from the combination of AND and NOT. That means AND plus NOT. Now, AND means A dot B. Apply NOT for the whole AND. That means A dot B whole bar. The next one is a NOR operator. NOR means the combination of R plus NOT. That's why A plus B whole bar. Next one, XOR. XOR also known as exclusive OR. So exclusive OR operator, this is the symbol of exclusive OR, A XOR B. The next one is XNOR. XNOR means XOR plus NOT. That means this is XOR whole bar. It is XNOR B. This is a dot and circle. This is the symbol of exclusive NOR. So these are the basic operators and the additional operators which we are using in Boolean algebra. Now let us discuss about the basic definitions for several operators and postulates. The first one is binary operator plus defines the addition operation. and also which is used to specify the OR operation in Boolean algebra. And the second point is additive identity is 0. What is meant by additive identity? When you add any number to 0, then it doesn't change the value of that particular number. A plus 0 means A itself. That means when we add any value to this identity, it doesn't change the value of the given number. That means 0 is the additive identity. The next one is additive inverse. Additive inverse means suppose if A is added with the same negative value, then it becomes as A minus A. This is nothing but subtraction. The next one is binary operator dot. Dot means which defines the multiplication and also which specifies the ANDing operation. In Boolean algebra, the multiplicative identity is 1. That means if A is multiplying with the sum 1, then only it doesn't change the value. If it is multiplying with any other value, then it changes the value. Okay. So that means the multiplicative identity is 1. That this is nothing but multiplicative identity. The next one is for A not equal to 0, the multiplicative inverse of A equal to 1 by A. Suppose if A is multiplying with 1 by A, then it becomes as 1. That means what? Suppose if A equal to 0, if we take, then it becomes as infinity. That's why we have to take the condition of A not equal to 0. That means the multiplicative inverse of A is 1 by A. Next one is the only distributive law applicable is that dot over plus. That means A dot B plus C equal to A dot B plus A dot C. That means the multiplication over these two B and C. Now let us discuss about axioms and laws of Boolean algebra. Axioms also called as postulates, which is having no proof. Now let us discuss about the one by one. The first one is the structure is closed with respect to the operator plus. That means suppose when we use the plus operator between these two set of elements, then the resultant also will lie in the same set of numbers itself. That means the structure is closed with respect to the operator itself. This is the first axiom. The second one is the element 0 is an identity element with respect to plus. Already we have discussed before, the additive identity is 0. That means if A is added with 0, then it becomes as A only. Similarly, if any variable is added with 0, then it becomes as the same variable itself. X plus 0 also equal to 0 plus x is equal to x only. This is nothing but additive identity. Similarly, multiplicative identity means x dot 1 equal to 1 dot x equal to x only. This is the multiplicative identity, just like A dot 1 equal to A only. Now let us discuss about the various laws. The first one is the commutative law with respect to plus. That means if we take the two numbers x and y, x plus y equal to y plus x. If it satisfies, this law is called as a commutative law. And also the commutative law which is applicable for dot operator. That means x dot y equal to y dot x. So we can use any of these two commutative laws while we are minimizing the Boolean equations or expressions. In the same way, the next one is the distributive law with respect to plus over dot. That means x plus y dot z equal to x plus y dot x plus z. Similarly, the next distributive law is x dot y plus z equal to, just we should multiply x dot y plus x dot z. This is already we know from basic mathematical algebra. This is obtained in Boolean algebra only. These two are very useful in the simplification of Boolean functions. Now, let us take one example here. Suppose if we have a plus cd. Now, we can simplify this one as a plus c into a plus d with the help of the distributive law. So, this is the way of writing the distributive law during the simplification of the Boolean functions. Now, let us move to the complement law. Complement law means x plus x dash. x is added with x dash. That means 1. So when we add the complemented value, the resultant should be 1. When we multiply the complemented value, it gives the 0 value. That means a plus a dash equal to 1. A dot a dash equal to 0. We can use any variable, any type of the variable. It doesn't matter. Only the matter itself is the normal form of the variable is r-ing with the complemented value, then it becomes as 1. If it is ANDing with the complemented value, then it becomes as 0. This is about complement law. The next one is there exist at least two elements such that x not equal to y. That means the set already has the binary value x and y that belongs to B. B means the set of the binary values should be x, y. Always these two should not be equal. That means 0 and 1 always we have to maintain. Okay, there exist at least two elements x comma y belongs to B such that x not equal to y. So these are the various basic definitions which we are going to use in Boolean algebra. Now let us discuss about the two-valued Boolean algebra. In this, the set of elements should be 0 and 1. That means the set is denoted with the variable B. Okay, now we should apply these two set of elements over the operators plus and dot. The first axiom is 0 plus 0 equal to 0. This is the addition. 0 plus 1 equal to 1 plus 0 equal to 1 according to the commutative law also. Now 1 dot 1 equal to 1. Next one is 1 dot 0 equal to 0 dot 1 equal to 0. Now let us move to the commutative law. Now we should verify these commutative laws with the help of the truth tables. The first commutative law over dot, the second one is over plus operator. Suppose if we take the first law, LHS equal to RHS, we can prove with the help of the truth tables also for the same set of elements 0 and 1. Now A and B as two inputs. With these two input variables, we can assign the four combinations of binary with a set of elements 0, 0, 0, 1, 1, 0, and 1, 1. Now, how can we write these sequence of binary values with two inputs? We can generate the binary means the radix is 2. With this radix value, with the two input variables, we can write the four combinations of binaries. Four combinations including 0 we have to write. That's why 0 to 3 only we can write. That means 0, 1, 2, 3. 0, 1, 2, 3 should be right in binary form depending on the binary weights. The binary weights are 2 power 0 and 2 power 1. Then 0, 0, 0, 1, 1, 0 and 1, 1. Now A dot B means AND gate operator. AND gate means if multiplication, just like multiplication. If one of the input is 0, obviously the output should be 0. If both inputs are 1, then only the output will be 1. This is the ANDing operation for the LHS part. Similarly, for the RHS part also we have to prepare. So B dot A means the first input is B, the second input is A. So that we have to change the sequence of the order of variables. B and A are inputs. Again, the total number of input numbers should be 2. So 2 power 2 combinations, again 4 from 0 to 3. Now we can find the multiplication operation. That means B dot A. If one of the input is 0, again the output will be 0. For the only last case, we will get the 1. That means the LHS part and RHS part both are same. That means the commutative law is satisfied over the operator dot. In the same way, over the plus operator, we can verify with the help of the truth tables. A plus B operator, the same truth table repeats towards left side. Now, A or B means if one of the input is 1, the output will be 1. Otherwise, the output will be 0. Similarly, towards right side, the first input is B, second input is A. Even though we change the sequence of the variables, Again, when both inputs are zeros, then only the output will be 0. If one of the input is 1, then the output will be 1. This is the ORing operation. Okay. So again, we can check LHS equal to RHS. That means the commutative law over the plus operator also satisfied. Now let us move to the associative law. The associative law says that A plus B plus C equal to A plus B plus C. That means we have to prove this associative law with the help of the truth table for the same set of elements, zeros and ones. To verify using the truth table, the first column indicates the number of input variables. We have A, B, C. With these three input variables, 2 power 3 combinations of binary we can write. That means 8 combinations, always starting from 0, so that we have to write the binaries from 0 to 7. So 0 to 7, we should write based on the 3 binary weights. The 3 binary weights are 2 power 0, 2 power 1 and 2 power 2. That means 1 to 4. So with the help of these 4 to 1 binary weights, we should write the binary values by inserting the ones in the corresponding positions of the binary weights. Now, based on these ABC combinations of each and every binary, we should write the A plus B first. A plus B means Ring of A plus B. Ring of A plus B means if both inputs are zeros, then only the output will be 0. If one of the input is 1, the output will be 1. So except these two cases, all the remaining combinations has at least 1. So the output will be 1. Now, after A plus B, then we have to Ring with the C. That means we have to concentrate only on C and A plus B columns. Now again, if both inputs are 0, then only the output will be 0 according to Ring operator. Now remaining all combinations has at least 1. That's why the output will be 1. So the final answer for the LHS part is this one. In the same way, for the RHS part also same. First, we should take the ABC and 0 to 7 combinations. And B plus C, we should write B plus C. Next one is after B plus C, we should Ring with the A plus B plus C. The same operation has to perform. So now we can check the LHS part output and RHS part output. Both are same. That means the associative law over the plus operator also satisfied. Let us move to the associative law over the dot. That means A dot B dot C equal to A dot B dot C. Now the same associative law can be verified with the help of the truth table. Now the input variables are A, B, C. Again, with 3 input variables, we have 0 to 7 combinations, totally 8, based on the 3 binary weights 1 to 4. Now, first we should finish the bracket part, A dot B. That means A dot B means ANDing operator, that is multiplication. Multiplication means when both inputs are 1, then only the output will be 1. Otherwise, the output will be 0. The ANDing output is 0. After finding the A dot B, then this A dot B has to ANDed with the C. Now we should concentrate only on C column and A dot B columns. When both inputs are 1s, in the last combination only we have both 1s. Then only the output will be 1. Otherwise, the output will be 0. In the same way, for RHS part also, we have to prove the same combinations ABC. Now we should finish the bracket part first, B dot C. Now A dot B dot C we have to perform. That means first we should finish the dot C. We should ANDed A with this B dot C. That means we should focus on A and B dot C columns. Again, we should check only the last combination has 2 1s. Now only we will get the 1. The remaining all combinations has the same zeros. Now we should check the LHS part and RHS part. Both are equal. That means the associative law over the dot also satisfied. In the same way, we shall move to the distributive laws with the help of the truth tables. The first law is A dot B plus C equal to A dot B plus A dot C. Without dot also we can write simply. The second law says that A plus B dot C equal to A plus B into A plus C. This is second distributive law. Both distributive laws can be verified with the help of the truth tables. Now let us discuss about the complement laws. The first complement law over plus is x plus x dash equal to 1. Second one is x dot x dash equal to 0. Now we should check these two complementary laws with the help of the binary values. Here we are using the same variable in both forms, in normal form and complement form. Now, if x equal to 0, we substitute. X equal to 0 means 0 plus 0 dash equal to 1, which is equal to 1. The R in between 0 plus 1 is 1. Similarly, suppose if x equal to 1, that means x equal to 1 means 1 plus 1 dash means 0, which is equal to 1 again. So, both gives the same value as 1. So, both gives the same value as 1. That means, for any value of binary, x plus x dash equal to 1. Similarly, we can write y plus y dash equal to 1. That means the same variable when we add with the complement of the same variable, then it gives the value is 1. Similarly, when we multiply with the same complemented value of the variable, then it gives the 0. This is already we have discussed in the earlier, verified with the help of the binary. If x equal to 0, when we substitute 0 dot 0 bar, which is equal to 0 bar means complemented value, then it becomes as 1. 0 dot 1 is 0. Similarly, if we use the x equal to 1, 1 dot 1 bar equal to 1 dot 0, which is equal to 0. That means both are same. Whatever the value of the x, which is multiplying with the complemented of the same variable x, then it gives the 0. This is nothing but a complement law. All these laws and theorems, which are very helpful in the simplifying of the Boolean functions. The next one is duality principle. These are basic theorems and properties of Boolean algebras. Okay. The first one is duality principle. What is meant by duality principle? Duality principle means interchange R and AND operators and replace ones by zeros and zeros by ones. Now let us take one example to understand this duality principle. A bar plus 1 equal to A dot 0. This is my Boolean equation. Suppose if I want to write the duality principle for this equation, now we have to interchange R and ANDing operators and also zeros and ones. That means A dash should be same as it is, plus should be replaced with the dot interchange and ones with the zeros, which is equal to A also should be the same. Dot is replaced with the plus, 0 with the 1. Now we should check what is the value of this equation. A bar plus 1 is 1, which is equal to A dot 0 is equal to 0. This gives rise to A dot 0 equal to 0, which is equal to A plus 1. That means its value is 1 according to the OR gate. If one of the input is 1, the output will be 1. If one of the input is 0, when we are applying the ANDing operator, the output will be 0. So now you can check both are same. That means whenever it needs in simplifying the Boolean expressions, we have to use the duality principle to convert the same expression into simple manner. So this duality principle will help in simplifying the Boolean operation whenever it requires to change the formation of the Boolean expression. Now we shall move to the postulates and theorems of Boolean algebra. There are several theorems and postulates we have, which are all these are useful during the simplification of the Boolean expressions. The first one is postulate 2. This is x plus 0 equal to x over the plus operator. In the same way, we should write it as over dot over. Okay, that means x dot 1 equal to x. Now, Using the postulate 5, x plus x dash equal to 1 over the plus operator, over the dot operator, it should be x dot x dash equal to 0. According to the theorem 1, x plus x equal to x dot x also equal to x plus 1 equal to 1, x dot 0 equal to 0. All these are already we have verified in the previous session. Okay. Now coming to the involution. Involution means x bar whole bar equal to x. Now commutative, associative, and distributive, all these are explained before. Okay. The next one is De Morgan's laws. De Morgan's laws means x plus y whole bar is equal to x bar dot y bar. Similarly, the second De Morgan's law says that xy whole bar equal to x bar plus y bar. The next one is absorption theorem. X plus xy, which is equal to x only. The first one is x plus xy, which gives, take the common x, then it becomes as 1 plus y. Then x is ending with 1 plus y means ORing of y with 1, that means 1, which is equal to the multiplication of x with 1 is x only. Now we can check the RHS part. Both are same. In the same way, the second one. The second case is x is ending with x plus y, which means according to the distributive law, when we multiply x dot x plus x dot y, this becomes as x dot x is x only, plus this is xy. Now we should take the common x, 1 plus y again. 1 plus y means again 1. That means x is ended with 1. Then it becomes as x only. Now we can check the x. So these two are the absorption laws means easily we can verify with the help of the previous theorems. Okay, let us see about the operator precedence. Operator precedence means when we are going to simplifying the Boolean functions, the priority of operations to be performed first. The priorities should be assigned to each and every operator. The first priority always given to the parenthesis part. The second priority is given to the not operation, that means complement. The third priority is adding. The fourth priority is ORing. These are the priorities of operators to be performed during the simplification of the Boolean functions. Now, with the help of these operator precedence, we should simplify the Boolean expressions to the minimum number of literals. Let us see one example. So this is one example, practice example. Let us take the given Boolean function like this. What is meant by Boolean function? The Boolean function means the combination of input and output variables, operators, and the equal symbol. This is nothing but a Boolean expression or Boolean equation. Now, in this equation, right side variables, we call it as input variables. That means x, y, z. These are 3 input variables. The output variable always towards left side only. That means f is the output variable. And the operators in this Boolean function are plus operator, dot operator, and complement operator. And one more operator is equal. Okay, equal symbol. So the combination of all these parameters are framed as a Boolean function. Now let us take the Boolean function and simplify to the minimum number of the literals with the help of the above axioms and theorems. What is meant by literal? Literal means if any variable is available in either complement or normal form in any number of times is nothing but a literal. That means, suppose if we take the given Boolean function, this is my given Boolean function. In this Boolean function, the number of input variables are A, B, C. The number of these are 3 input variables only. The output variable is only 1 variable. Whereas the number of literals should be, we have to count. This is first literal, x dash. This is second literal. This is third literal. 4, 5, 6, 7, 8, 9, 10, 11, 12. So the number of literals should be 12. That means each and every input variable, it can be available in either normal form or complement form in any number of times in each and every product is nothing but a literal. Now, here what is our aim? The simplification of Boolean functions has to simplify to get the minimum number of literals only. The reason is, suppose if we take the given Boolean function, when we draw the circuit diagram, it requires 1, 2, 3, 4 AND gates, 1 plus operator or OR gate, 4 input OR gate, and for X bar and Y bar, it requires 2 NOT gates. So it is little bit complex. The circuit is complex. When we simplify with the help of the axioms and postulates, then we will get the only simplified answer. That means the equivalent value of this given Boolean expression should be f equal to z. Z means it doesn't need any logic gate. Okay, just a simple operator, that is the buffer. If z is the input, directly it gives the same value itself. So it reduces the circuit complexity and the cost also will reduce, and the number of wiring connections also should be reduced. So this is the beauty of the simplification of the Boolean functions. So now we should see one example in this session. Now we should see one example. So this is our given Boolean function. Now should try, is there any common variable in any of 2 or more product terms? Here, when we see these 2 terms here, x dash z is common. That's why x dash z, these 2 are common. Then the second variable is y dash plus y. So y dash plus y. And out of these 2, the common variable is x and z. Again, x and z take common. Y plus y dash. What is the value of y dash plus y? Its value is 1. Already we have seen in the previous theorems. Y dash plus y equal to 1 only. This is the complement law. X dash into 1 into z. So the multiplication of this one, that means when we multiply, what is the multiplicative identity? A dot 1 equal to A only. That means whenever we are multiplying any value with 1, the same number itself is obtained as output. That means here we are multiplying x dash z with 1. That means x dash z. Similarly, xz. Again, out of these 2, z is common. Take common. X dash plus x. Again, x dash plus x is 1. Now, 1 dot z. That means, again, it gives the multiplication. The resultant should be z. That means only 1 literal we have. So this is the simplified answer for the given Boolean function. So in spite of all these logic gates with the complex circuit, just we should get the, with the help of the above axioms and theorems, we will get the simplified circuit diagram. The diagram is simply one buffer, that is z and z. Okay, this is the simple circuit diagram. Okay, so this is about Boolean algebra, the fundamental topic, which is very useful for competitive exams also. And I hope you understand these concepts very clearly. So I have explained these topics in detail. The reason is, for GATE examination or competitive exams or any interviews, the conceptual analysis is very important. That's why I have explained very clearly in this topic. Thank you.